So I will speak today about atomic force microscopy and conductivity analysis of inkjet-printed electrode structures. This is a topic which is mainly interesting for only printing of electronics, but atomic force microscopy of inkjet-printed electrodes or structures can of course be also of interest for any kind of inkjet-printed patterns on surfaces. The work has been performed for the atomic force microscopy by the co-worker Mr. Narcifoso, who is also present in the conference, and you can visit him at our stand outside. And the second part of the talk about the conductivity analysis has been performed in a collaboration with the Technical University of Sofia during the last year. Our methods which we use for the field of optical electronics or organic electronics and also photovoltaic cells are mainly electrical probing. We use an electrical probing system with micro robots where we can use 2-point or 4-point measurements to be precise on the positions. And we have as a structuring methods, we have a microplotter who is can be used for continuous inkjet printing of, for example, lines of different materials like organic molecules or even also nanoparticles. So let's come to the first example, atomic force microscopy. We used silver nanoparticle inks and wanted to see how these lines are formed and how the curing process, the thermal curing process, takes place. For this, we do curing at relatively low temperature. This allows them to see really the involvement of the structures. So main investigation which we do is that we look in an optical microscope the printed lines, and that then we were interested in looking at the nano and microstructures at different positions on the line profile or along the line, in the center and also at some other regions. The structures we observe are typically scans of 10 times 10 micrometers or even smaller, 5 to 5 micrometers. The line widths which we can print with our plotter are here, for example, 130. Typically, they range between 70 and 150 or 200 micrometers, depending on the viscosities and substrate and so on. What we see here are the nanoparticles which are starting agglomeration, and we look at roughnesses. Analysis of roughnesses is a statistical analysis on different positions along the lines to have average values. What we see here are some bigger particles which have already formed during 1 hour of curing. And we have roughness which is not exactly the same along all the line. At the border, the roughness is smaller. In the middle, it is even smaller, and we have higher roughness at an intermediate part. When we heat further, the situation changes a bit. Roughness overall increases, but we see that it becomes more homogeneous on the full line structure, and we get a broader line with roughness values, and the particles, they become also a bit bigger. And then we can also look after 6 hours, for example, of curing, to see how the structures really evolve with time. And we are now currently ongoing with the work to correlate these structures with conductivity measurements, which we do on these printed lines. So I want to come to conductivity measurements and how we perform them. We work mainly with organic thin films, and then the critical issue is really how to measure conductivity of very soft material. Already measuring conductivity is not an easy task, because normally you can come with 2 electrical probes. If you do it only with 2 electrical probes, you will have resistance of your probe. You will have contact resistance contacting the layer. So often in electronics, also in semiconductor industry, for example, people use 4 probes. 2 probes to have the current, and then 2 other probes to measure the voltage drop in between, which increases already the precision of the measurements and which avoids these questions of contact resistance and resistance of electrical probes. However, although we can use commercial 4-point probe heads, they are not always suitable for these soft materials to measure really conductivity in a reliable and reproducible way, because you come with your probe and you don't know how much you dig into your surface. And if you really apply the same force, so you start damaging easily these soft materials. So our main message today is that we have developed the test structure and the method how we can circumvent all these problems of the mechanical damage. And this is finally a method which can be applied to analyze really the conductivity of polymer structures, of soft materials, and this means also of ink layers, for example. The interest was in the P.PSS, which is a material used in organic photovoltaics, for example. And there's a lot of interest not only to use it as a whole transport layer, but also to use it maybe as a transparent electrode to replace maybe the indium tin oxide, where the problem is the indium which is not available in big parts on the Earth. So conductivities of indium tin oxide are our goal value, and they are about 1,330 Siemens per centimeter. They have a high stiffness, then conductivity measurement is easy. But P.PSS, one finds in literature very different values. They can go higher with doping, but the stiffness is low, so electrical probing is really not straightforward. So the goal is now to have the test structures or a method to measure the conductivity on such soft layers, to analyze conductivity, and then also to see how is the UV degeneration. Is it stable under UV, or can we improve the stability of these organic layers with doping effects, with some dopings? The electrical measurement method which we have put up is inspired by a technique which is used in semiconductor electronics, where generally you deposit metal lines on the semiconductor to have then a geometry of transmission lines, which is a method which allows to eliminate contact resistance. We don't want to evaporate on our films, inkjet printed or spin coated films, the electrodes, but we want to have a structure which still is transparent and which can be used also easily, maybe in industry, when using just a test structure to deposit the material onto it. So we use as electrodes rather underlying electrodes, and we use transparent electrodes. So we form electrodes from indium tin oxide. We have used test structures with 7 indium tin oxide electrodes, and we deposit the P-dot layer on top of it and use then a 2-point probing method. We use one electrode probe on the first electrode, and then we change the position of the other probing electrode, but we always contact on the indium tin oxide, and we never touch mechanically the polymer layer. So this is one of the test structures, and we need for the calculations afterwards, we need a second test structure which finally has only the external electrodes, and we can also measure there. So it is a 2-point probe measurement, but we use measurements at different distance, and this will then allow to extract the electrical values. I will not go now to the very, very details, but just to explain, one can then model the structure with an relatively simple electrical model, looking in the cross-section what we have as a structure, and model each part with the resistance. So we have here a resistance from the polymer, and we have here resistance where the current can go through the indium tin oxide, but also to the polymer, which is even a bit smaller. So this is our elementary unit, which will repeat in our structure 6 times. And then we might have a constant which can come from all kinds of interface resistances or even the contact resistance at the border. Then we have our second test structure, where we can also model the elements. We again find the resistance for the polymer and we have always, in fact, the resistance of the polymer. And the external structures is the same as in the first structure. So we can note down what is the equivalent resistance in this test structure and also in our other test structure, calculate the difference. And from our measurements, which come from one distance, the second distance, and so on, we can plot the values of the resistance as a function of distance, find a linear dependence, and the slope of this graph will finally enter into our model, and we can at the end extract really what is the resistance of the parts containing the polymer. It's really simple mathematics at the end, and from this we get information, or really direct information, about the resistivity, conductivity, and sheet resistance when we know the layer thickness, of course, from our deposited polymer. The layer thickness we measure generally with optical interferometry, also to have not mechanical damage. So we have a test structure and a method which allows to study thin layers of polymers, so can be used for inks. The second advantage is that the full structure is transparent, so we can use the structure also to measure how it evolves when we expose it, for example, to light. So we can directly measure by measuring these resistances, we can directly measure online how the electrical properties evolve by time. No electrical probe makes a shadow on our polymer, so we can directly measure the behavior. This we did. So we studied the exposure of UV light. We used a UV light source of 254 nanometers with an intensity of 8.8 microwatt per centimeter square. And we observe that, in fact, the resistance increases by time. So this means that there is a decrease in conductivity and there is some degradation when we expose the P.PSS to UV. The values which you see here are already the better case. In fact, we doped our P.PSS with dimethyl sulfoxide, and this increases it dramatically by a factor of 1,000. One finds this in literature, the conductivity of P.PSS. So this is already a good case. And this is known from literature. Here you have the reference that the doping effect is the improvement of the conductivity. And overmore, we find that the conductivity degeneration factor, so by time, is about 2 times lower compared to the P.PSS without doping. So it also improves the stability of the full layer. And the conductivity values which we get at the end for the doped P.PSS are comparable with conductivities of indium tin oxide. And now the main point will be to improve the UV stability. The other point which we studied, of course, also is the evolution of the structure of the surface structure of our polymer layers. The roughness increases when we expose it to UV, but this is the case for both structures, and currently we are investigating more in detail what are the effects taking place at the microscopic level. So as a summary, we have on one hand the electrical characterization method put in place with a test structure which is suitable to test inks on the conductivity. We have no mechanical damage, a full transparent structure, and we have found with this method that we can really exclude the contributions of the contact resistance and electrode resistances. So it really is reliable to measure conductivity of soft materials. And with doping of the P.PSS, we have succeeded not only, as already known, to improve the conductivity, but also we have found out that the UV stability improves by about a factor of 2. And our main issue is now to study, in general, to study inkjet printed structures at the atomic force with the atomic force microscopy to know more about the nano and microstructure parts in such inkjet printed electrodes. Thank you for your attention.
Thank you very much, Silvia, for your excellent presentation. Are there any questions from the audience? Yes, please.
You showed that surface roughness goes up on exposure to heat and UV. What's going on chemically that's causing all this?
Yeah, personally, I don't know what is going on. So we would need some collaborations to study if some changes in the chemistry takes place, or if it is still related to maybe solvent which was initially still available in the layer, if it was not fully dried, or what really is the origin. We have not the tools to do this. Thank you.
Yeah, other question?
How do you think, what is the reason of conductivity increase for P-dot PSS in the presence of DMSO?
Okay, there are some papers about these topics. It's an effect of secondary doping, which takes place in these organic molecules, or with these organic molecules. What exactly are the charge transport mechanisms behind is not fully understood at the moment. But it might be related to some improvement of charge hopping processes or something like this.
Thank you.
Thanks. Yeah, other question?
Thank you, Frank Amter. It was a good presentation, actually, and would like to know the influence, if the moisture absorption of the P-dot has any influence, and secondly, about the contact resistance, as you mentioned also in your presentation, and with other layers underneath, like, for example, screen-printed silver lines instead of ITO, or inkjet-printed nano-silver lines instead of ITO.
Yes, I did not get the first part of your question.
Influence of the moisture of P-dot?
Okay. So these measurements have been done in normal conditions, in fact. So we have not really looked at humidity effects. And concerning the interface resistance, our model can be completed with a resistance about the interface resistance between the indium tin oxide and the coating layer, but it would also be eliminated by the subtraction of the two test structures. So we would not get it with this test model information about this. However, about barrier heights, we are currently measuring also the IV characteristics of layers which are deposited one on the other, and then you can get out Schottky barriers and so on between the barrier heights between different layers.
Okay. We would still have time for one more question if there are.
Or maybe one comment more, because there was the question about contact resistance. Okay. So in principle, when you look just at such a graph, then it would be somewhere here would be a link in information about the contact resistances, which can play a role there. So from the graphics, of course.
Okay, so thank you very much.